Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will discuss basic electrical characteristics of the Mosfet. In the previous class, if you recall, we discussed how a Mosfet is a barrier control device, and the barrier is visualized if we draw the band diagrams of the Mosfet. So let me quickly review what we have seen so far. So these are the band diagrams in absence, or these are the band diagrams of the source region, the channel region and the drain region, when assuming that they are not connected with each other. And if in an actual MOSFET where the source, the channel, the drain are actually connected, this is how it looks like. In the previous class, what we saw was that we have a gate terminal here, and if we apply a positive voltage on the gate terminal, this barrier height actually reduces. This barrier height goes down. So that way this gate voltage can control the barrier height. Also we saw that if we apply a drain voltage, then what happens is that this drain side conduction band goes down, and the symmetry of electronic concentration around the barrier is also disturbed. Okay, and so by applying a gate voltage or a drain voltage, we can change by applying a gate voltage we can change the barrier height itself, and by applying a drain voltage we can change the probability of crossing or electrons crossing across the barriers. Okay. So, and because of this property of the MOSFET is also known as a barrier controlled device. That is because of this property of the MOSFET. So this is the application of the gate voltage on the MOSFET, and if we apply a drain voltage, it will change the Fermi level as well, and the equilibrium is also disturbed, and in this case in steady state this is how it will look like. So the application of a drain voltage does not change the barrier height in an ideal MOSFET. It does not, and in conventional MOSFETs it does not actually change the barrier height, because on the source side the voltage is still 0, on the drain side the voltage is Vd, let us say. So this height which depends on the voltage across the channel, and on the left side of the channel the voltage is still around 0, so that is why this barrier height does not change. But as we go from the left to the right side, the voltage increases from 0 to Vd, and that is why this barrier is now barrier changes in this way. This follows the potential profile across the channel. Okay. So this is the case when only the drain voltage is applied, but in addition to drain voltage, if gate voltage is also applied, is also there, in that case this barrier height is reduced, and because of the drain voltage we have more or we have this barrier height which is more on the drain side. So that's why now we can see that more number of electrons from the source side can cross the barrier, and there will be a current from the drain terminal to the source terminal. So that's how this IDS will start in the MOSFET. Okay, and that is essentially the mechanism of current conduction in the MOSFETs. So this we have already seen from our previous class. This comes from a simulation actually. This is taken from a book by Mark Lundstrom, and here what happens is that the VDS voltage, the voltage difference between the source and the drain terminal is assumed to be 0.05 volts, and by changing the gate voltage or for various gate voltages, the barrier in the device is shown basically. And as you can see that by changing the gate voltage we can actually change the barrier height, and after a certain point actually, so let's say so this is the source side, this is the drain side, this is the channel region, and gate voltage is changing the barrier height, and there are electrons, since source is n-type material, so there are electrons sitting on the source side, and drain is also an n-type material, so electrons are also sitting on the drain side in this way, let's say. So initially if the barrier is this much high, and even if we apply a small drain voltage, even if we have a small VDS which is around 0.05 volts, there won't be any current in the system, because the probability of these electrons crossing the barrier is extremely small, because this barrier is too high for these electrons to cross. Similarly, the probability of these electrons, the electrons on the drain side, to cross the barrier will also be extremely small. It will be even smaller than the probability of electrons sitting on the source side. Okay. But as we increase the gate voltage, this barrier height is reduced. Now this is the barrier, but even now it is extremely difficult for the electrons on the source side to cross the barrier. Similarly for the electrons sitting on the drain side. If a more gate voltage is applied, this will be the situation. So the barrier is, let's say, now here. Now you can see that the energy of the electrons here and the barrier height, there is very less difference between the two. So then the probability of crossing the barrier will now be some non-zero value. It will be some. So now some current will at least start in the device, because there is a drain voltage. So if we apply slightly more drain voltage as well, in that case the probability of electrons on the source side to cross the barrier will be more as compared to the probability of electrons in the drain side to cross the barrier. So there will be a net current. So as you can see that the current only starts after a certain gate voltage in these devices, and if we further increase the gate voltage, now the barrier height is actually less than the energy of the electrons on the source side. So now it is not at all difficult for the electrons on the source side to cross the barrier, and if we apply a drain voltage, in that case it will be relatively more difficult for the electrons on the drain terminal to cross the barrier, and there will be this non-symmetric crossing of the barrier, and that's how a current will be starting in the system. So as you can see that after a certain gate voltage, only after a certain gate voltage, a significant current starts in the device, and that gate voltage is known as the threshold voltage. Okay. Before the threshold voltage, if the gate voltage is less than the threshold voltage, in that case the current is very small. So if we have the MOSFET like this, we have the source terminal, the drain terminal, the channel region. Just above the channel we have oxide, and on top of oxide we can put gate. So if the gate voltage is positive enough so that it can help create, or it can create an inversion layer of electrons just below the oxide, in that case only the current will start in the system. Okay, and so the voltage at which this inversion happens properly in this channel, that voltage will be known as the threshold voltage. So below the threshold voltage, if the gate voltage is less than the threshold voltage, in that case an extremely small current is there. It's not that there is no current, because even when the gate voltage is less than the threshold voltage, there is a finite probability for electrons to cross the barrier. So there will be, but the current will be an extremely small current, and below threshold voltage it is known as the sub-threshold current. So it is the sub-threshold current that is there in the system. Okay, and this region or this regime of operation, when the gate voltage is less than the threshold voltage, this is known as the sub-threshold regime. Okay. So that is essentially the transistor operation. So the transistor operation can be summarized in this way, that it is about playing with the barrier in the device, and this is done by applying a gate voltage. So the gate voltage has contribution in changing the height of the barrier, and the drain voltage has a contribution in having asymmetric distribution of electrons around the barrier, and that way a current is actually started in the system. So now so before going into the current expression, there is one more point that I want to sort of remind you, that in conventional MOSFETs, what happens is that generally we have source, we have drain, we have a small oxide here, and we have a gate here. So there is a positive voltage in an NMOS, there is a positive voltage applied on the gate terminal, the source is grounded, there is a positive voltage applied on the drain terminal as well. VD and VG is positive. Okay. So now the threshold voltage is the voltage that is applied on the gate terminal, so that this inversion layer can be formed inside the channel. But as we apply a drain voltage here, a drain voltage also creates a potential profile in the channel, which means that now the net voltage difference between the gate and the channel on this side, on the drain side especially, is now less than so the voltage difference between VG and let's say VC, the channel, or let's call it Vx. So on the drain side especially, it might be less than the threshold voltage, especially on the drain side. So if a positive drain voltage is applied, it will in a way nullify the effect of the gate voltage, and that way the channel or the inversion layer in the channel towards the drain terminal might not be present, and that is known as the pinch off in the channel, or pinch off region of the channel. Okay. So this is just to remind you that because of the drain voltage, the effect of gate voltage is also disturbed in the channel. If there is no drain voltage, in that case this gate voltage creates a uniform effect across the channel, but if there is a drain voltage, the effect of the gate voltage is now non-uniform. On the source side, we might have a very good inversion layer, but on the drain side the inversion layer may be weak, or there might be a pinch off at all. So this pinch off is essentially the depletion region, like the depletion region in the PN junctions. And so the channel with when the drain voltage is high, in that case the channel consists of an inversion layer and a pinch off region. Okay. So all those things need to be taken into account while calculating the current, or while trying to understand the electrical characteristics of the current. So there are two concepts that I told you. One is the notion of the threshold voltage, that is the gate voltage at which significant current starts in the, or significant current can start in the device, which means that is the gate voltage at which the channel is, or the inversion layer is formed in the N MOSFET. Okay. And second is the notion of the pinch off. Now let's try to understand the current inside the device. So ultimately we have, the MOSFET is like this: we have source, we have drain, we have the channel, and but in addition to this, this is actually 3D thing. This MOSFET is a 3D entity. So okay. This is how it looks like. Okay. A general expression of the current from the drain terminal to the source terminal, because typically we apply a positive voltage on the drain terminal. So generally source is grounded, so the voltage applied on the drain side is known as the VDS voltage. And apart from this, we have a channel region, also we have an oxide layer here, and on top of that we have the gate terminal actually. So this is the gate terminal. So the voltage applied on the gate terminal is known as the VGS voltage. So now, because of the, as we have seen, because of the drain voltage and the gate voltage, this is how the band diagram will look like, and this will create sort of a charge profile in the channel. So the charge profile in the channel will be dependent on VGS and VDS. So the charge per unit area, so because now this channel, this inversion layer in the channel, that is like a quasi 2D channel, that's like almost like a 2D thing. So the charge per unit area, per unit cross section area, that is represented as Qn, and this Qn is a function of both VGS and VDS. Okay. So this is one important parameter while discussing the MOSFETs, that is the charge density or the sheet charge density inside, the charge density in the channel. Okay. This is the charge per unit area. The units can be coulomb per meter square. Second is, the second important thing is the velocity of the charge carriers. So this charge is because of the electrons in the case of N MOSFET, because of the electrons in the inversion layer. So the number of electrons, as we have also seen during our discussion on the transport theory, that the number of electrons depend on the applied voltage. So the number of electrons in this case will depend on both VGS and VDS, and the velocity of electrons crossing this barrier actually will depend on the electric field ideally, and typically this velocity is the velocity of charge carriers. The most important velocity is the velocity of the charge carriers at the top of the barrier, at this point actually, also known as the, in some cases this is also represented as Vt. So that if we have the charge density or the number of electrons in steady state in the channel, and we know that how fast this charge is getting eliminated from the channel, how fast this charge is moving through the channel, then the current will be given by the product of the charge density and the velocity and the width. So this is a very general definition of the current, and this is true for any arbitrary device. This is not true just for the MOSFETs, because in any device, if we have a charge distribution, if we have a charge density, and if we also know how fast that is moving, the current through that device will be given by the multiplication of the charge density with the velocity, and we also need to multiply by the width. Okay. So this is a very general form of the current in the MOSFET, that is given as the multiplication of the charge density and the velocity at which the charge carriers are getting eliminated from the system. Now let me slightly point out here that since a positive voltage is applied on the gate terminal, so this barrier height from the drain side is actually, the barrier is very high. Barrier height increases from the drain side. Barrier height is more from the drain side as compared to the barrier height from the source side. Okay. So most of this current is because of the electrons crossing the barrier from the source side. So almost all of this current is because of the electrons crossing the barrier from source side. Okay. So please keep this in mind, and that is why and if we sort of want to see this velocity, here we have written the average velocity, but if we try to understand this velocity of electrons crossing the barrier from the source side, so just in the beginning they encounter this barrier peak, this peak of the barrier, and at the peak of the barrier the electric field, what is the electric field at the peak of the barrier? So at the peak of the barrier we can see that or if we take the gradient of this curve, del V by del X, this is 0. So the electric field tends to 0 at the peak of the barrier. So this is the velocity of charge carriers in absence of any electric field. So this is the velocity just because of the diffusion of the charge carriers without any external influence of the electric field. In a way, this is just the thermal velocity of the charge carriers. So, the velocity at the barrier height is without any electric field, and velocity at any other point. So, for example, at this point there is an electric field in the channel. So, there is a positive voltage on the drain sides which will attract electrons. So, the velocity will be more at this point as compared to the velocity at the top of the barrier. So, in a way, the limiting factor in current is the velocity at the top of the barrier in the channel, because at all other points the velocity is almost always more than the velocity of electrons at the top of the barriers. So that is why in most of the cases, instead of this average velocity, generally we use Vt term in order to calculate the current in a MOSFET. Okay. And this charge profile, the charge per unit area, is actually because of the application of the gate voltage and the drain voltage. So, now with this general form of current, now as you might have already guessed that there are two distinct things here. One is this charge distribution, the charge inside the channel. Second is the velocity at which this charge is moving through the channel. And generally this is the understanding this velocity is a subject matter of the electron transport theory. So, if the electrons are scattering with particles in between, this velocity will be, we will need to take into account the scattering of electrons. If the electrons are directly going from the source to the drain side, from the source to the drain terminal, as we have already seen, if this is a ballistic MOSFET, in that case this velocity will be known as the ballistic injection velocity. So, understanding this velocity is actually the subject matter of the transport theory, is the subject matter of the electron transport, and this charge profile inside the MOSFET is because of the application of the gate voltage and the drain voltage. This is typically the subject matter of the electrostatics, or this depends on the electrostatics inside the MOSFET. Okay. So, essentially in order to understand MOSFET physics, in order to understand the electrical characteristics of the MOSFET, we need to understand the electron transport through the system, and we need to understand the electrostatics in the system here. The transport part we have covered fairly well already. So, we will use that knowledge here in the MOSFET physics, and after this basic discussion we will briefly see, or we will briefly discuss about the MOSFET electrostatics as well, and that way we should be able to understand the entire physics of the MOSFETs. Okay. Nowadays, because of the scaling, because now the size of the MOSFET is reducing, nowadays the transport is changing fundamentally, because in conventional transport theory the diffusive transport is assumed by default, but it is no longer true, because nowadays the channel length is smaller than the mean free path of electrons, and nowadays ballistic transport is quite common. So, this needs to be revised properly, and that was one of the major goals of this course. Electrostatics is more or less, the fundamental principles of electrostatics are the same, they are not changing, but the way it is playing role is nowadays slightly different than in long channel MOSFETs. In short channel MOSFETs, the electrostatics physics, the physics of electrostatics does not change, the principles of electrostatics do not change, but the way this manifest is changing slightly, because nowadays we need to take into account the 2D electrostatics properly in the MOSFET. Okay. So, so this is the mobile sheet charge in the device Qn, V is the velocity. So, magnitude of the current depends directly on the width as well. More the width, more will be the current. Velocity is the purview of the transport theory, and the Qn is the in the purview of the electrostatics. Apart from these things, and this we have already sort of highlighted, I have already highlighted this, that the application of the gate voltage does not affect the Fermi level in the channel. This we have already seen, because the electronic distribution does not change on application of the gate voltage. That is why the Fermi level is maintained, and that is why this equilibrium, the equilibrium is also maintained in the system even when a Fermi level is, even when a gate voltage is applied. So, this now brings us to sort of understanding the IV characteristics of the Mosfet. Okay? And this is the source terminal, this is the drain terminal, this is the channel region, this is the gate terminal. Electrons are flowing from source to drain side. So, the current will be flowing from drain to source on application of drain voltage and gate voltage. So, the relationship between IDS and VDS is known as the output characteristics of the Mosfet. At a constant VGS. So, now in the light of the entire discussion that we had, this barrier dynamics, how this barrier changes on application of VGS and VDS, then I would like you to think about the output characteristics of the MOSFET, IDS versus VDS, in the light of this entire discussion that we have had. What would be the form of IDS versus VDS for a MOSFET? So, I will let you think about this, and we will discuss about this in the next class. I thank you for your attention and see you in the next class.